So one of the important properties of waves is how they interfere with each other. And one of the one of the sort of wave phenomena that you run across, and in fact in music you run across this all the time, is dealing with standing waves. And so standing waves are produced when two waves with identical frequency interfere with one another while traveling in opposite directions in the same medium. So basically what you can imagine is I've got a way down here that I'm creating a wave, and so that's this blue wave that travels to the right, and then it hits this end and reflects back as this red wave. And if I have exactly the right frequency coming through this, right? So if my frequency of oscillation is the right frequency of oscillation, giving what the speed is for the wave to be able to travel through this medium, then I can actually get standing waves. I get standing wave patterns. And so when I look at a standing wave pattern, there are a couple special points that I need to recognize. One is, again, the wavelength. So the wavelength is what's the distance it takes for my wave pattern to repeat. So here I start by going up, come back down. Here's where I'm about to start going up again. So from this point to this point, that's my wavelength. I also could have measured it from crest to crest or trough to trough. In each of those I would have gotten exactly the same distance. The other thing that for a standing wave pattern, I get places, special places where there's no displacement, right? So no displacement away from my center line. And these are called nodes. So the nodes are the points where there's no displacement. And then the places where I have the maximum displacement, these are the antinodes. And so you notice in this particular pattern, I have a closed end. So I have what's known as a fixed end, standing wave. All that means is that there's no disturbance. I'm forcing a node at this point and a node at this point. And so when I count up, I see that I've got 1, 2, right? 2 humps makes a wavelength. And I've got 1, 2, 3, 4, 5, 6 humps. So I've got 3 wavelengths worth of wave here. So there's 1, there's 2, there's 3. So we'll come back in terms of labeling that in a second. But what I notice here is that, so I've got 6 humps, which means I have 1, 2, 3, 4, 5, 6, 7 nodes, and 1, 2, 3, 4, 5, 6 antinodes. And that's a pattern that we'll be able to see pretty clearly over the next couple of slides. So that's the basics with standing waves. And then there's 3 different types of standing waves that we can set up. And the first one is standing waves between 2 closed or fixed ends. And so this, the most common standing wave of this type that you run across is on a stringed instrument, so something like a guitar. And so I can pluck a guitar string and end up with these kind of standing waves because the guitar string is fixed at both ends. And so you'll notice that, again, you can sort of count up the humps. There's 1 hump here. That's the first harmonic, n equals 1. There's 2 humps here. This is the second harmonic, n equals 2. 3 humps gives me the third harmonic. 1, 2, 3, 4 humps gives me the fourth harmonic. 1, 2, 3, 4, 5 gives me the fifth harmonic. So the first thing that I can do is just count up the humps. The next thing I can notice is, well, for my first hump, 1, 2 nodes, 1 antinode. When I've got 2 humps, I've got 1, 2, 3 nodes, 2 antinodes. 3 humps, 1, 2, 3, 4 nodes, 3 antinodes. So you see the pattern very quickly here that I'm going to have for my closed end standing wave. The nth harmonic is going to have n plus 1 nodes and n antinodes. And then the last thing that I want to pay attention to is, well, again, counting up the humps, I need 2 humps to make a wavelength. So I've only got 1 hump here, so that tells me that this is half a wavelength. I've got 2 humps in this next one, that tells me that this is a full wavelength. So when I think about the length of this string and how it relates to the wavelength, well, I get that for the first, my first harmonic, this length of the string is just half a wavelength because I've only got one hump. For my second harmonic, it's a full wavelength because I've got two humps. My third harmonic, I've got 1, 2, 3, so I've got one full wavelength plus another half. So this tells me I've got 3.5 wavelengths sitting in my length of string L. For the fourth harmonic, I've got 1, 2, 3, 4 humps. That's 1, 2, one wavelength, 3, 4, a second wavelength. So I see that I've got 2 wavelengths in L. We can keep on playing this game, and what you'll notice is that basically there's a pattern that's setting itself up here. So this was the first harmonic, 2L over 1 gives me that answer. This was the second harmonic, 2L over 2 gives me L. Third harmonic, 2L over 3. Fourth harmonic, well, let's see, 2L over 4 is the same thing as L over 2. Fifth harmonic, 2L over 5. And so what the pattern is it says that the wavelength of the nth harmonic on my string length L is going to be 2L divided by whatever the number for your harmonic is. So this is what we see in a closed standing wave. Next, if I've got a open, right? So here's an open end, here's an open end. So this is the kind of standing wave that we often see in something like an organ pipe, right, where I've got 2 open ends in the pipe. And so what you'll notice here is the open end means that's an antinode. The open end means that's an antinode. So for my first harmonic, I've basically just still got one hump. I've just kind of cut it in half so that the antinodes are now at the end and the nodes in the middle. So I see that for my first harmonic with an opened standing wave is I've got 2 antinodes and 1 node. For the second harmonic, I've got 1, 2 nodes and 3 antinodes. Third harmonic, 1, 2, 3 nodes, 1, 2, 3, 4 antinodes. So I get a different pattern here if I've got an open standing wave. In this case, I get, for my nth harmonic, I'm going to have n nodes and n plus 1 antinodes. Now, in terms of the bumps, it's the same thing, right? So my first harmonic really has one bump. It's just that it's cut it in half and sort of switched the order. My second harmonic has got one bump in the middle, and then again here's the on the ends gives me my second bump. Third harmonic, 1, 2, 3. 1, 2, 3, 4 for the fourth harmonic. So the pieces on the end for my open wave are always making up an additional bump, and so you can count the rest of them, add that one from the 2 that split on the end, and that's the easiest way to just see what harmonic you've got, right? It's just count the bumps, just like it was with our closed. Again, if I want to think about the wavelength, well, for L, same thing's true here. I've really just got one bump in my first harmonic. One bump means I've got half a wavelength, so my distance L here is just half the wavelength of my wave. Here I've got 1 plus 2, or plus a second, so I've got 2 bumps, so I've got one full wavelength here, right? It's starting at crest, comes down to trough, comes back up to crest, so sure enough that's a full wavelength. So here L is equal to the wavelength of the wave. For my n equals 3 harmonic, again I go, there's one full wavelength plus another half, so I got 3.5 wavelengths. For my n equals 4, there's one full wavelength, there's 2 full wavelengths, so L is equal to 2 wavelengths. For n equals 5, I see that it happens to be 2.5 wavelengths. And so again, we can solve these for lambda, for the wavelength, and we get the same pattern that we did with our closed, right? So whether I have two open ends or two closed ends, I actually get the same type of pattern, right, in terms of the wavelength, how the wavelength relates to the length of the standing wave. How I can change that is actually by going to the one closed, one open. So this might be something that you have in, say, a horn, where you've got a closed end to where your mouth is blowing, and then you've got an open end at the other end of the horn. So when I've got one closed and one open end, what I'll notice is a couple things. One is I don't have a full bump here. I've only got a half of a bump. And a half of a bump is another way of saying a quarter of a wavelength. So here I've got a bump and a half, two bumps and a half, 1, 2, 3 bumps and a half. So you notice that I only actually get odd numbered harmonics. When I have my one closed, one open end, my harmonics are only odd numbers now. So I've got n equals 1, but there's no n equals 2. Next one's n equals 3. One after that's n equals 5, then n equals 7, then n equals 9. So these are just the way that we number when we've got one closed and one open. Now, in terms of the wavelength, well, again, what I recognize for my first harmonic is that this is just a quarter of a wavelength, because it's just half a bump. This is, I've got a bump plus a half a bump, so this is 3/4 of a wavelength. Here's a full wavelength, right? That gives me 2 bumps all the way through a wavelength, but then I've got another quarter left over. So this is 4/5. Over here I've got 1, 2, 3 bumps, and another half. So this gives me one full wavelength here, and then I've got 3/4 of a wavelength here. So this is 7 lambda over 4. Here I've got 1, 2, 3, 4 bumps plus a half. So I've got 1, 2, there's a full wavelength. 1, 2, there's another full wavelength. Plus, I've got a quarter of a wavelength left over. So you see a similar pattern, except for what's changed is instead of being 2L on top, now it's 4L on top. And the only ends that I can plug in here are just odd numbers. So here I can only use n equals 1, 3, 5, 7, 9, unlike with my closed, closed, or open, open, where I could use all integer values, 1, 2, 3, 4, 5, 6, etc., etc. So these are the 3 types of standing waves that we'll deal with, and we'll play with some problems in class thinking about these standing wave patterns.